Alright, so welcome to the first video of advanced functions. Today is going to be a somewhat short video. We're just going to go over some basic stuff about functions, mostly review. Maybe there's going to be a few new things here. They're mostly going to be just small things that may become important as we go through the course. But definitely, this is definitely like the very first lecture where we will have some new stuff going on. So, I want to start by discussing just some random sets of numbers. So, numbers, when you start counting, like when you're a kid and you start counting, you start with 0, 1, 2, 3, and then you go as far as you want until you get tired. These are sort of your first counting numbers, and we call them the natural numbers. Okay? And for these, you may know that we write a blackboard N. It's just an N with an extra little line on the vertical. Then, what you can do after the naturals is take the negatives of all of them, and you'll get the integers. Those are integers, and we'll call them Z. And this ZI thing, it comes from the German, so like there's no reason why Z should be used for integers other than that's what the German word for integers starts with. The next thing that you can do is take fractions. So when we take fractions, we want them to be in reduced form. We don't want unreduced fractions like 4 over 2. So we have the set of all fractions a over b, where a and b are elements of the integers, right? So this is notation for elements of the integers, right? And what else? We also want a over b to be in lowest form. So a over b is in lowest form. Okay? And this is a set that we call Q, also German. These are our rational numbers. Okay, so rational. Okay. So rational numbers, they all look like that. Now the question comes, I said we don't want things that look like 9 over 3 or 4 over 2. Right? So we can't have those in here. Those are not rational numbers. So in fact, where do they belong? So that's actually a point that's somewhat up for debate, and really it depends on who you're talking to and what the context is. That doesn't really matter for this level of math, but just putting it out there. You may think that because of the way fractions are made, you get like a chocolate bar or something, you divide it in half, and then you divide each half in half again, and then you can get like really, really small parts. And so you might think that maybe I can get like every single number this way just by taking my 1 and dividing it into these parts like a fraction. And that actually turns out to not be the case. One famous example is the square root of 2. The square root of 2 was known to the Greeks to be a very special number. We call this an irrational number, and its main importance, there are many, many applications of the square root of 2, but perhaps the most basic one is if you take a 1 by 1 grid and you look at the length of the diagonal, it's square root of 2. It's just like Pythagorean theorem. So this is definitely not some random abstract number that we decided to come up with just to give the rationals trouble. This is something that we actually have to deal with in everyday life. So, of course, because the square root of 2 doesn't fit in the rationals, and there's a whole proof for that, we have to invent a new set of numbers. And luckily, this is as far, and this is the end of numbers for 99% of the population. And they're called the real numbers. It's a nice name. So really, the real numbers is just everything that fits on the real line. Now, if you're really paying attention and thinking about everything that this sentence says, you will be very dissatisfied, because this is a circular definition. I'm saying a real number is on the real line. So how do I know something's on the real line? Well, look, the problem with this is that in order to really define what a real number is, you need a lot harder math. And that's kind of outside the scope of this text, this course. So this makes a real problem, because every function that we're dealing with in this course is a real function. That means it takes in a real number and it outputs a real number. What does that even mean if we don't know what a real number is? So this is a problem, a really big problem, that that the curriculum kind of glosses over. And for the sake of ease, I'm going to gloss over it as well. However, you should know some of the typical examples of real numbers. So, what things fit on the real line? I can give you examples, for sure, I can give you examples. So, all the rationals definitely fit on the real line. We also have any radical expression, square root of x, right? Where x can be in Q, right? Any of these, they also fit in the real line. Some other examples include pi, e. You know, like the point is, there's a lot of them, and you should at least get a feeling for which numbers are real. Now, here's the question: is there something that's not real? I mean, does there exist a number that is not real? That's a perfectly valid question to ask. And it turns out that there is. There are a lot of numbers that are not real. Now, we are definitely not in curriculum anymore. I am just going to mention this briefly, and you don't really have to know it. It's just a fun little thing. You can go into complex numbers. Okay, so here's a number that is not real. Square root of -1. Okay, so the square root of -1, you may have heard before that if you do this to your calculator, it says very bad things, and it doesn't like it. In the complex numbers, this is not an issue. The square root of -1 actually has a place. It's called I. And every complex number looks like A plus BI, B times I. And I mean, that's it. That's it. So really, all you're doing in the complex numbers is you're adding in this new letter I, and I represents square root of -1. Square root of -1 is not in the reals, so we've successfully added something to the to real numbers that is not in the real numbers. Okay, but this again, you don't really have to know. Okay, so let's just go over again the definitions of functions, and we're going to go over some domain and range examples that may be a little more complex than what you may have seen in grade 11. So just to remind you, a function is a way of assigning elements in one set to another. That's all it is. It just has to follow one rule. And the one rule is one element can only be assigned to one other element. And so I'm sure you're familiar with examples like, okay, here's a quadratic x squared, right? It's a function, but if I take the function that is both root x and negative root x, this is no longer a function, it fails the vertical line test. Okay, so all I've said here is that you cannot send one element in your domain to two things or more. Okay, you can only set it to maximum one thing. Okay. In fact, really, I should put at most one other element. But I'm going to assume that this definition is familiar enough to you, given that the grade 11 course is literally called functions. So now we have domain, right? So this is the set of elements that we are taking and sending and assigning to another set. So this is like your x-axis, right? It's the set of elements that get assigned values. Okay. The other one is range. Now, for some reason, everyone's fine with domain, but range is where it starts to get confusing. Range is your y-axis, but just like how x-axis isn't totally accurate for domain, y-axis isn't totally accurate for range either. And we're going to see some examples of that. Okay, but the range is the set of values for which the function assigned an element in the domain. So the set of values for which the function assigned an element in the domain. Okay? So let's go over some tricky examples. So of course I'm going to assume that you're aware of the basic ones that are covered in grade 11. Those would be things like the quadratics, linears, trigonometric, exponentials, and so on. And even rationals and rationals is the other big one. Okay. So here is an example where the domain and range is not just everything. Okay, it's not very difficult to draw one of these. Look, here's a rational function, and for the sake of argument, let's just call this 1 over x. Okay, so this is the function 1 over x, and well, what is domain? It's the set of values that this function assigns to something. Okay, well, I can see here, and maybe I should make this more explicit, because this is a vertical asymptote. It never touches the y-axis, it just goes as close to it as possible and just misses it. So, the domain is the set of elements that this function sends to something in the plane, right? So we're going to look at all the x values, and notice that everywhere the function will send that x value to something else. Okay? The only part where there is a problem is here. At this point, x equals 0. So we have that at x equals 0, we have the function does not assign any value. Okay? And what this means is that 0 is not in the domain. I'm just going to write dom is not in dom f. Okay? Similarly, you can play this game for the range. So we're going to look at all the y values and see that everywhere the function f assigns that y value some coordinate in x. The only exception is y equals 0, right? So this is the line y equals 0. And the function never hits the x-axis, y equals 0. So at y equals 0, the function never assigns a value x to 0, right? So in other words, f of x is never 0 for all x in the domain. Okay. So what we're going to do is we're going to say that 0 is not in the range. Okay. So maybe that is a little tricky to see at first. Maybe it's really easy. I'm really not sure what your level of understanding of this stuff is. But in any case, I have developed, for myself at least, I don't know if this is this makes sense to other people, but I've sort of come up with a foolproof way of finding the domain and range every single time. So if you apply this trick properly, you'll never get this question wrong. This question of what is the domain and range of this function? And believe me, that is a question that will come up several times in advanced functions. It's not something that is so elementary that it's not worth asking anymore. So here's how it works. Here's how my trick works. What you do is you get your function, okay? It looks like, let's just make it a little more complicated this time. It's gonna do this for a while, and then it's gonna jump up here. It's gonna jump up there. And let's say it does something that looks like a cubic. And then well, let's see. Let's give it another break. Right here, right here. And it just goes straight. Okay? So we want to know what is the, actually let's make it, let's do that. Okay. So I want to find out what the domain and range of this function is. So here's how I do it. I imagine I'm shining a light down here, and I imagine I'm shining a light up here. And basically, what I'm doing when I'm finding the domain is I'm looking where this light hits the function and casts a shadow on the x-axis. So here's the x-axis. Remember, all of the points in the domain are going to lie somewhere on the x-axis. So what you can do is you can imagine these like beams of light that go and hit the function, but whenever they hit the function, it casts a shadow. So here it casts a shadow, it casts a shadow, it casts a shadow everywhere here, and over here what happens? What happens? Well, the light can go through completely. So you may think, oh, this section here is not part of the domain. Well, that's why we have the other light on top, right? So the other light on top is going to go through, and we're going to do this. Okay? Now, what this means is that everything in here is in the domain, and everything here is in the domain. Okay? The only thing here that might be a little tricky is this little point here, because what happens is that the light will hit this point, and this point will block the light, and that casts a shadow here. So in other words, what all this means is that this point, this x value, is in the domain. We're going to keep going here. We're going to keep casting our shadows. Okay? And then we're going to continue from here, right? Now you notice this point here is missing. And all that means is that the light will be able to pass through it completely. And if we look up here, there's nothing on the other side as well. So this means that the function never assigned this x value to anything. So in other words, this point right here is not in the domain. Okay? And really I'm talking about the x value that's right there, this x value. Right? It is not in the domain. Okay? Hopefully that makes sense. If it's not, we can talk about it a little bit more, but this is just my way of trying to explain domain and range in a very easy to check way. It might not work for you. So really, at the end of the day, it's up to you to find the strategies that work for you best. I'm just proposing something that you may never have seen before. Okay. I'm going to redraw this picture so we can talk about range. Where do I want to draw this? Let's draw this here. I'm going to go to the other side in a sec. All right. So now the question is range. What is the range of this function? Okay. So what I'm going to do is I'm going to do the exact same thing as I did before, except now I'm going to shine lights on the right and the left. Okay, so let's see what that looks like. I'm going to shine a light here. I'm going to shine a light here. Okay, we'll just get this out of the way. Okay, and we're going to do the same game. We're gonna cast shadows and see what happens. Okay, so here is just like a bunch of stuff, right? A beam of light cannot pass through here, so it's going to cast a shadow, just like that. Okay, and okay, yeah, that's fine. That's fine. Here is going to keep casting shadows, right? And of course, up here, right, it's going to cast shadows as well. There's like two obstacles in the way of the light getting to the y-axis. Okay. Now, when we go over to the other side, the situation changes. So I'm just going to draw these lines here. And look, we're still casting shadows. At this point here, this point is solid, so it casts a solid shadow here. All this means is that that point is in your range. Okay. And this point was in the range as well. And then over here, well, look, there's no function here. There's no function to block the light. So, I mean, all these points are getting illuminated, but that doesn't really matter because they were already, you know, they already had a shadow here. Okay. Now I'm going to keep going. I'm going to keep casting my shadows here, here, and now there's two obstacles. And as soon as I reach up here, well, there's nothing, right? So there's nothing there. Okay, maybe I should have made it a little bit more explicit. Now I'm realizing. I'm just gonna. Okay, well let's just keep it like that. So we're gonna say that those 2 points are at the same height. So this point and that point, they're at the same height. Okay. Okay, hopefully that's clear. Okay. And now, what has this gigantic mess shown us? It's actually just highlighted for us the range, just like that. So obviously these lines, they continue forever here, right? So what we have is that every number below here is in your range, and every number between here and here is also in your range. Everything else is not in your range. So that means every point above this and every point between these two, they are not in your range. Okay? So that was a little bit more of an abstract example. We are going to work with more concrete ones, and ones that will actually require you to graph the function sometimes in order to see it. It's very difficult to just immediately say, oh, of course, that's the domain, that's the range. The exception is basically every function that you've learned so far, they've been defined almost everywhere. Maybe rationals, they might be the sole exception, but for the most part, the functions that you've been working with have been very nice with your domain and range. And we're going to work with a specific class of functions that does its hardest, its absolute hardest to mess you up on this. Okay, so the first example that we're going to work with is sine 2x minus 1. Okay, now you should be able to graph this from your grade 11 knowledge. I'm just going to quickly graph it right now. If you're not super comfortable with this, I would ask you to pause the video and try and graph it yourself and make sure it looks exactly like this. Okay, so all we have is at -1, this thing is going to go up and down, up and down, up and down. It's going to hit, oops, that's wrong. Go up and down, up and down, up and down. And it's just going to continue that forever. Its low point is at -2, and its high point is at 0. So it just goes between 0 and 2, 0 and -2, 0 and -2, and we know it hits -1 there. Okay? Domain, it should be fairly obvious. You can use the trick that I just showed you. Just shine a light over here, and you'll see that every point on the x-axis is going to get shaded. Okay? So I just drew a bunch of lines here, right? And you can totally do this, but it's probably going to make your tests and images look really messy. So I suggest just doing it with your eyes. after you get some practice with it, it shouldn't be so hard. So now so the domain is literally everything. So domain is all of R. So I'm just going to write the Blackboard R for reals. Range, we can do the exact same thing. And I encourage you to try if you have your graph drawn out. You should be able to see, either using the trick that I've shown you or just from your previous knowledge of functions, that the range, and I'm going to do this in set notation. So the range is the set of all y, such that y is a real number, and y is between -2 and 0, including -2 and 0, because here it does intersect -2 and it does intersect 0. So it intersects -2 and 0. Okay. Now, I kind of sneaked this in here without mentioning anything of it before. This is, of course, set notation. And I know you're familiar with this one, so I'm not going to really dwell on how to write this a lot. The only thing I will say is that teachers tend to be very picky about their set notation, depending on how they learned it. The way I learned it was in such a way that you can define your set like this. Y is an element of R, and then you just have to specify which elements of R you're really looking at. But it's okay to write the big set R in here. I know some teachers don't like that. This is like the very, very technical right way of doing it, but pretty much everyone I know writes it like this. So just pick one, and whatever your teacher says when you're doing this course in the real term, just stick with that. So yeah, that's all I have to say about that. Okay, let's do the next example, and we'll do it in interval notation. From my experience, people tend to be a lot more comfortable with interval notation than set notation. So the next one is, okay. So what about this? X to the 4 plus x cubed plus x squared plus 1. Yikes. Yikes. We really don't have anything to graph this other than Desmos. So, I mean, if you want, you can pop up Desmos and just try and figure it out yourself. But what I'm going to do for now is I'm going to say, let's put this aside. We're going to work as a goal to getting this done within the next week. We are actually, in the next week of work, we're actually going to be able to graph things like this and then find out their domain and range, literally just by graphing them. Okay? The only thing that you could probably tell right now is the domain. Sorry, domain. The domain is easy, right? You just have to think about it, and you think about it a bit, and you think, well, the domain is really all the sets of all the x values that I can put in here, and there won't be any problems. That happens to be every single real number you can think of, because the really nice thing about these polynomial functions, maybe you've heard the word polynomial before, but if not, then this is an example of a polynomial function. These polynomial functions, they're defined everywhere, and they never cause problems. You don't get like 1 over 0 type of problems, or you don't get square roots of negative numbers. These are very, very nice functions. So for now, all we can say is that the domain is everything. The range, we'll just leave a big question mark there for now. Okay. So instead of that, let's consider a little bit of an easier polynomial. Let's consider x squared. This is like a really comfy, homey polynomial that you've been with since grade 10. Just very quickly, try to figure it out on yourself. Pause the video and then just check if we wrote down the same thing. Okay, and we'll do this in interval notation. So domain, range. Now this might seem like a very easy exercise, but really the whole point of this is just to be able to write this in interval notation. So in interval notation, you have to write -infinity to infinity. You may have had teachers stress this, that you can't put an equal sign here because x can never actually equal -infinity because -infinity is not a number. So don't put an equal sign there. little subtle point that teachers will be very, very picky about. The range, of course, it hits here at y equals 0, and if you use the flashlight trick, everything above here is going to be shaded forever. Okay, so that means that the range goes from 0, equal sign, that should be a y, to infinity, not equal sign. Okay, little tricky stuff here and there, and these will cost you if you forget these. So this is an easy example, but it's just to highlight that there are these subtleties that you sometimes have to look for. Okay, so here's one other one that should be a little more interesting. We're going to take f of x to be this. Let's do this. Okay. So, depending on what you did in grade 11, this might seem a little insane. What is this? Is this even a function? Like, I've never seen this before. This is the example that I mentioned earlier, the type of example that will absolutely try and mess you up with your domain and range. These are called piecewise functions. They're called piecewise functions because they're defined on pieces, right? So here we have 3 pieces. We have a piece of the function that is everything before -1. We have a piece of the function that's everything between -1 and 1. And we have a piece of the function that's everything after 1, including 1. So what I'm going to do now is graph this so you can see the process of how this piecewise function definition gets translated to the actual graph. So what this rule is telling me is that for every x less than -1, so let's just draw -1 here, and while we're at it, I'm just going to draw 1 as well. We want the function f of x to equal to -1. So let's just draw that. I'm going to draw this in red. Okay. So here's the point, -1. And for every value of x from -1 and lower, this is going to be my function. It's going to be a straight line. It's just the function y equals -1. Okay. What next? In purple, I'm going to draw the next piece, and this can take us from -1 to 1. Okay. This is the function x. X is a very easy function to draw. It's just a diagonal line that goes to the origin. Okay? The key point here is that it actually meets the other function, -1, right at this point. Maybe you dream that every function defined this way will behave like this. It's nice. It's like connected together. This is not the case. I could have very easily just added a 1 here, and this little x component would have been dragged up a little, and then it's no longer connected. So this is where these questions become a little trickier. Okay. So now the next thing that we're going to do is the last part, which is everything after 1, including 1, is x squared. So x squared at the value x equals 1 is just, well, 1 squared is 1. So that means it actually meets the function x at x equals 1. And it's just going to look like your typical parabola. Okay? So this is the piecewise function. Okay? As I've said, it looks really connected and nice right now. Usually it doesn't work like that. Usually you get into a lot of trouble. But because this is the first time, and this might be the first time you've seen this notation, I've decided to pick an easier example. So let's go and find the domain and range of this. If you use the light bulb trick that I've been sort of advertising this whole time, you will find that the domain is simply everything. And one really easy way to look at it is to just actually look at this part. Because all of these functions are fine, and they're defined on everything from -1 and below, between -1 and 1, and everything after -1. There's no value of x that has been missed. So the domain is everything. I'm just going to write R, depending on what notation that you're being asked to use. This might not be the exact one that you have to use. Also, I just realized I made a huge brain fart. I said interval notation for the previous example. What I really meant was inequality notation. So because of that mess up, let's do this one in interval notation. So that just about finishes everything that I wanted to talk about today. There's only one other thing here that maybe I want to mention, which is that this really nice property that we had where the red line connects with the purple, which connects with the brown. This is a special property that we're going to continue exploring, I believe, in 2 lectures from now. It's a property called continuity, and it's going to be so important that it even carries over into calculus. So just intuitively, I think you can see what's going on here. They're just like connected to each other, but we'll make this more precise as we go through the course. And especially we're going to be interested in how can a function be continuous and what happens when it's not continuous. Like, what does it mean for a function to not be continuous? Yeah, so next lecture we're just going to be simplifying more complex expressions. So it's really just going to build off of the factoring that you learned in grade 11. Some of it's going to be review, but we're going to be taking a couple of ideas to the next level, and we'll be able to tackle bigger expressions and more complicated expressions.